Today we are discussed about three-moment equation. Three-moment equation is an express the relationship between moment and the successive supports and the load on the two spans. That means this three-moment equations deals with the an equation made with moment and as well as the load. And it also considered as an unequal settlement of supports. That means three-moment equations containing using that three-moment equation we can find the settlement also. Then it is derived from the consistency condition that slope at the middle support calculated from left span should be the same as the slope at the middle support calculated from the right span. That means consistency condition means you have only three equilibrium equations and you have to find more than three unknowns. It is very difficult to find the unknowns. So three equation we can only identify using that three equation. You can only calculate that three unknowns. If the number of unknown is greater, so you must want some extra equations. So that extra equation we can call it as consistency conditional equation. So we for these equations we apply some other conditions or some other equation for solving this type of problems. Then this equation is called consistency equations. So the three-moment equation in this three-moment equation means in that we have three supports. The definition itself says that it have three successive supports and two spans. That is the condition for three-moment equation. Then next part we are go through the derivation part. In this derivation we consider the three supports and two span. And after sometimes the support A and support C settled. And settlement of support A and support C as HA and HC. And B is the middle support. So the consistency condition means consistency condition is in this case is the theta value on the left hand side is equal to the theta value on the right hand side. That is our consistency equation. So you can use additional equation or additional you will get an additional equation in addition to our three equilibrium equation. So this consistency condition, using this consistency condition we can derive an expression and that expression is called our three-moment equation. For the derivation of three-moment equation we consider these three diagrams. In this diagram, first diagram deals with the moment due to external load and second diagram deals with the moment due to fixed supports. That means here we have three supports. First fixed end moments, that is three supports, support A, support B and support C. Support A is a hinged support, roller support. Support B is hinged and support C is roller. Using these three supports, there is some moment produced in these three supports and the support moments we can call it as fixed end moments. And the fixed end moments we can in this diagram it's shown that MA, MB, MC are the end moment diagram and it is act as a pointed loads. So it is the variation of bending moment as linear. But in previous case load is considered as UDL. So the curve is like this. It is a second order equation. So the diagram like this. So for this derivation we consider the moment diagrams two types, that is first diagram due to external load and second diagram due to foundation. For the calculation and all we have to identify some terms. Here some of the important terms you have to discuss are first one, span of the beam AB L1 and L2 is span BC. I1, I2 are the moment of inertia and HA and HE are the settlements. Then A, B, C dash and A2 dash B, C2, these are the lines drawn in this figure. Here we can see that line ABC. Initially the B lies at A dash B C1. After some time it reaches at A and C1 reaches at C. And this distance is settlement. Here the B is the common point and there is no settlement takes place in this B. So we can draw a line tangents to the point B, and this tangent line meets at A line as A2 dash and C as C2. So we can draw the figure like that. And some more in second figure we have MA, MB, MC moment at the supports, and third figure we have moment diagram on span BC and AB, where A1, A2 and A1 small a2 are the distance area of moment diagram in span AB, and A2 is the area of free moment diagram in span BC. Then small a1, small a2 are the center of gravity of that moment diagram. Here we already discussed as in this case we consider the consistency equation as our theta value, that is theta on the left side of B is equal to theta on the right side of the B. So we can take that theta, check that value. How do you find theta value from this figure? We can find it by consider the small triangle here. Similarly here we have also a small triangle. So we can take tan theta here. We will get A1 dash A2 divided by length of the B. Similarly tan theta again we can write it as C1 C2 divided by LC. This is our expression. So we can write that expression like this: A1 A2 divided by L1 tan theta, C1 C2 divided by L2. Here A1 A2 we want to write that A1 A2 in terms of HA. So from this figure we can see that what is HA and HC. We want the expression A1 A2, the small distance. So we write that expression as HA minus A2 A1. Here A2 dash A is the deflection. That means the tangent from the B and point at A. This makes a distance, and that distance is our deflection of that B. Okay. Similarly here B makes tangent of B makes at C2, and theta is equal to C1 C2 divided by L2. Here we want an expression in terms of HC, so we can write C2 minus HC, where C2 is the tangent, so C2 is the deflection. From this expression we can write HA minus A1 dash A2 dash is equal to HA minus A2 dash. A2 dash is the deflection, and the deflection we can find using moment of M by A diagram. There are a lot of methods to find the deflection. In this derivation we can use this moment of M by A diagram, because we already have two moment diagrams. Then next step, find the moment of M by A diagram. Here we divide the segment into three. Here first one A1, consider the span AB. A1 is the moment diagram due to UDL, and this portion we can split into two triangle A3 and A4. Then moment of M by A diagram means you have to draw the moment diagram, then find the moment of that moment diagram. So first of all find the area of this diagram, then multiplied by that centroidal distance. So the equation become A1 into A1 plus A3 into this distance, then A4 into that distance. So we can write that expression like this here, then divided by EA, then this is our expression, and replace the A3 and A4 as half. This is triangles, so half MA-L1 then half MB-L2, like that. Then rearrange all the terms, you will get an expression. Similarly the C1 C2 have some more values, and then you can find that values Similarly, we can consider the span BC. Then here A2, A5, A6 are the areas and corresponding distances are there. Then we write that A5 and A6, these are two triangles. Then rewrite, you will get an expression. Then our initial expression is these two are same, that is our values tan theta is same for both sides. So next step we check or we equate these two values. Equate these values, you will get this equation. Then equating and rearranging, finally you got an expression. This expression is called our three-moment equation, and the three-moment equation containing MA L1 by I1 plus 2MB L1 by I1 plus L2 by I2 plus MC L2 by I2, that is equal to minus 6A1 A1 divided by L1 I1 minus 6A2 A2 divided by L1 I2 plus 6HA divided by L1 plus 6EHC divided by L1. Here first three terms deals with the fixed moment values, and second two terms right hand side you have two expression deals with the load or moment due to external load, and third portion consists of our settlement values. This is our three-moment equation. You can use this equation for the analysis of continuous beam only. You cannot use this for columns or framed structures or trusses. It is applicable only for our continuous beam. So it's also called Clapeyron's theorem. So using the main advantage is used for the analysis of continuous beam. Thank you.